Okay, so in this final video on nomenclature, we're going to take a look at, continuing to look at compounds that contain hydrogen, but now we're going to actually focus in on a particular type of compound known as acids. So one thing I actually forgot to mention in the previous video, and it works perfectly fine to add it in right here, is that whenever you're looking at a compound that contains hydrogen in it, and hydrogen is written at the beginning of the formula, it's really important that you look at what state of matter that it's in. And the reason why is because knowing the state of matter that a particular compound is in is going to affect the name, because it'll actually have different properties depending on what state of matter that it's in. So binary compounds, remember that means compounds containing two elements that contain hydrogen as one of the elements, and then the second element either being a halogen or an element in group 6A other than oxygen, in their pure state have different naming conventions. That was a mouthful. So let me try to break that down a little bit clearer. So first of all, it's basically saying when you have a binary compound in which hydrogen is the first element, so hydrogen and then blank. So something is going to fill this spot right here. And whatever that second thing is, it could be a halogen, or it could be an element from group 6A. The reason why it excludes oxygen is because if oxygen was here, and then of course you need two hydrogens to balance out that oxygen, what is this? Obviously that's water. So that's why it's saying, okay, exclude oxygen, because oxygen has its own separate naming convention. So if hydrogen is bonded with a halogen or any other element other than oxygen in 6A, and it's in their pure state, which a lot of times the pure state means it's in the gas form, then it's going to be named essentially like an ionic compound. So let's just look at some examples so you'll kind of see what I'm talking about here. So HCl, a couple things to note. It begins with hydrogen, and a lot of you may be tempted to think if it begins with hydrogen, it's got to be an acid. Well, you need to take a look at the state of matter. It's gas. Okay, so HCl, the pure state of HCl is actually the gas form. So do not name this according to acid rules. You need to name this according to ionic rules. So instead of saying hydrogen monochloride, according to the rules we learned in the covalent video, we would just say it's hydrogen chloride. HBr. HBr, it looks like it could be an acid, but once again, look at the state of matter. It's a gas. Okay, so HBr, the pure state of HBr is the gas state. And so we're going to name this according to, once again, ionic rules. So instead of saying hydrogen monobromide, we're going to say hydrogen bromide. Finally, H2S. Notice S is an element from group 6A. There's two hydrogens, but the reason for that is because sulfur has a negative 2. That's why there needs to be 2. But nevertheless, H2S, it's in the gas form. So that's its pure state. And so we wouldn't name this dihydrogen monosulfide or anything weird like that. We would literally just name it hydrogen sulfide. I kept saying pure state, pure state, pure state. How would you know if these are acids? Because a lot of you probably thought looking at these that, HCl was hydrochloric acid and so on and so forth. The reason you'll know that they're an acid is because the state of matter is going to be listed as AQ, which means aqueous. So let's actually get into that right now. So we're now looking at acids. Acids are their own group. They have their own naming conventions. And so how do you know that you have something that's an acid? Well, first of all, let's talk about what makes something acidic. And so we're going to focus first on a binary acid. So by now, hopefully you realize that binary means two elements. A binary acid is a compound that contains hydrogen and another element, but here's the key thing. It's in the aqueous phase. And this is why it's the key thing, because when a compound that contains hydrogen and another element is dissolved in water, and that's what aqueous means, when it's dissolved in water, the hydrogen is going to dissociate. It's going to ionize. It's going to pop off, and you're going to end up actually producing hydrogen ions. It's the hydrogen ions that make something acidic. That is actually what makes something very dangerous to spill on your hands. It's those hydrogen ions. And so HCl, when it's in the gas form, the hydrogen hasn't popped off yet. It hasn't ionized because it's in a pure state. So that's why we're going to call it hydrogen chloride. But when HCl is dissolved in water, kind of like what you see down here in the picture, if you drop those HCls in water, they're going to ionize. And so it's going to produce all these hydrogen ions that you see here. And that is what makes it acidic. And so if you see HCl in the aqueous form, now you know to name it according to acid rules, because now it's in the acidic state. And hydrogen chloride and hydrochloric acid have different properties. So that's why it's important to name them differently. Okay, there's two ways to go about naming acids, and you can choose whatever you want. The first way is the rote memorization. You can easily Google a list of acids, and you can just start committing them all to memory. That's one way to do it, and you'll certainly be fine doing that. However, if you ever forget what an acid name is or how to name an acid, knowing how to name them can help you in a bind. Versus if you just memorize things and then you get yourself all confused, that might prove problematic. So I'm going to teach you how to name a binary acid. That way, if you ever need to do it on the fly, you're able to do it. So how to name a binary acid. And remember, what is a binary acid? It's hydrogen bonded to some other element. That's it. So how do you name that? Well, first of all, let me add here, it needs to be in the aqueous phase. Because if you see it in the gas phase or anything else, you know not to name it an acid rule. Okay, so when you see this, the first thing you're going to do is you're going to change the hydrogen part to hydro. Now notice the hyphen here because we're going to add something to hydro. Hydro is just the prefix. What you're going to do is you're going to take the root of the second element. So whatever this element is right here, you're going to take the root of that element and you're going to add it to hydro, and then you're going to change the ending to ic. So that was kind of a lot. We'll look at an example here. And then always you'll end with the word acid. That's obvious enough. So let's take a look here, HBr. Notice we saw HBr previously on this slide right here. When HBr was in the gas phase, that was hydrogen bromide. But now we're looking at HBr in the aqueous phase. And so that tells me that this is going to be an acid. So we're going to take hydrogen, and we're just going to keep the hydro part. We're going to get rid of the GEN. We're going to add on to that the root of the second element. Well, the second element is bromine, or bromide, whatever, but we're going to keep just the root part, which is brom. And then we're going to change the ending to ic. And we're going to take all three of those parts, this first part, this second part, and this third part, and we're going to put them all together to create the word hydrobromic. And then we're going to end with the word acid. And that's how you do that. You just do those three steps right there. So let's take a look at some examples. Let's take a look at naming and writing all together. So hydrofluoric acid. So remember, first of all, when I see acid, immediately I know it starts with hydrogen. And it's always the hydrogen at the beginning of the formula. That's actually the one that ionizes to make it acidic. So it's always written first. So hydro, okay, fluor. Fluor is the root, remember? So what element does that come from? And that's fluorine. And then it's an acid, so I need to make sure that it has the AQ. Now before you're done, you need to make sure that these two species right here cancel out to be zero. Because remember, they're ions. That's what makes it acidic. It ionizes. And so hydrogen is always +1, and fluorine is -1. And so having one of each actually is good. That's going to make it cancel out. And so never leave the charges. I just showed that there. So HF with an AQ is going to be your formula. All right, let's take a look at this second one. This time we're given the formula, asked to write the name. So I have hydrogen at the beginning, and I know that it's aqueous, and so I'm looking at an acid here. So I notice it's a binary acid, because that I only have hydrogen bonded to an element. Doesn't matter that I have 3 hydrogens, it still is 2 elements. That makes it binary. And so the rule is, take that hydrogen and turn that into hydro. Add the root of the second element. The second element is phosphorus, so I'm going to add phosphor. Okay, in terms of acids, the root is phosphoric, because then we're going to add the suffix ic and make it all one word. So it's hydrophosphoric. And then finally finish up with the word acid. All right, let's take a look at one more. So we have hydrosulfuric acid. It is an acid, so it tells me it's going to start with hydrogen. The sulfuric, notice that sulfur is a weird one. We actually include the whole word. We don't include just the root. So it's sulfuric rather than sulfic. And sulfur comes from S. And then it's an acid, so we need to make sure it's AQ. Now be careful. Always check to make sure that they are balanced out. Hydrogen is +1. Sulfur is actually -2. So whether you do T-chart or crisscross, doesn't matter. The idea is you need 2 hydrogens to balance out that 1 sulfur. And so let me get rid of my charges. And so my formula there would be H2S. Okay, so now those were binary acids. So remember, binary acids are hydrogen bonded to just an element, and it's in the aqueous phase. There are also what's called oxo acids. Sometimes people call them ternary acids. They are the same thing. And what are these acids? These are acids that are going to contain oxoanions. And you're like, what the heck is an oxoanion? An oxoanion is an anion that contains oxygen, which most of the time is a polyatomic ion. Because if you think about it, most of our polyatomic ions actually contain oxygen in them, like nitrate or sulfate. And so these acids are going to contain hydrogen bonded to not an element, but they're going to be bonded to a polyatomic ion. So notice, for example, nitrate, this oxoanion, will bond with hydrogen to make HNO3. Sulfate will bond with hydrogen to make H2SO4. And the reason why there are two of them is to balance out the charge of sulfate just like we would have before. So you're going to continue adding hydrogens just like we did before to the beginning of the oxoanion until the net charge is 0. So that's just like we did before. Okay. Once again, you can memorize these or you can understand how to write them so that way you can apply it to anything. So here's one of the key differences between binary acids and ternary or oxo acids. First of all, you do not start with the prefix hydro. That doesn't mean that there's not a hydrogen in the actual acid name. If I go back, you can see that these acids right here, they both are acidic because they have the hydrogens at the very beginning. But in terms of the name, they do not start with hydro. And so this is key. That is how you can tell immediately from the name of the acid whether it's a binary acid or whether it is a ternary acid or an oxo acid. Because binary acids start with hydro. Polyatomic acids do not. So what do you start with? Well, we're going to go to right here to step 2. Step 2, we're going to start with the root of the polyatomic ion, just like we would have if it was an element. Now, we can't just end everything in ic like we did with the binary acid, because if you remember from polyatomic ions, there's a lot of polyatomic ions that sound the same. For example, nitrate and nitrite. So nitrate is NO3 and nitrite is NO2, and both have a -1 charge. If you were to take the root of both of these polyatomic ions and just add ic, you would have nitric for both of them, but chemically speaking, they're not the same thing. So there has to be a way to distinguish when you're looking at polyatomic ions that sound very similar, like nitrate and nitrite, or sulfate and sulfite. So here's the rule. If the polyatomic ion ends in ate, then you're going to change the ending to ic, just like we always did. I like to think if you ate it, it would taste icky. It's stupid, I know, but it works. If the polyatomic ion ends in ite, you're going to change the ending to us. I have nothing clever for that one. Sometimes I like to think, oh, you want to party with us? Ite? Okay, that's stupid. It doesn't work very well. I got nothing. But nevertheless, that's how you can remember it. So, and then you're going to add the word acid. So the two main differences between the polyatomic acids and the binary is step 1, do not start with hydro. And 2, you're going to have different suffixes that you'll have to pay attention to. So let's look at an example. H2CrO4. You're like, whoa, that is a lot of craziness. Don't freak out. Okay, remember when there's a lot of elements in a compound, that usually is telling you there's a polyatomic ion in there. And there is CO4, that's a polyatomic ion, chromate. Here's the key thing I want you to see. It begins with hydrogen. So that should tell you that it's an acid. I actually should have the AQ here. So that's actually my fault. But when you see hydrogen at the beginning of a compound that contains polyatomic, it's an acid. And so here's the thing. We're not going to start with hydro. So the hydrogen just completely goes away. There is no hydrogen, there's no hydro, there's nothing. Just get rid of it. Instead, we're going to start with the root of the polyatomic ion. So remember I said the polyatomic ion is chromate, so the root of that is chrome. So now you need to change the ending. Is it going to be ic or is it going to be us? Since it's chromate, remember if you ate it, it tastes icky. So we're going to change it to chromic, and then we're going to end in the word acid. And so notice the name. It's chromic acid, not hydrochromic acid, chromic acid. So if I see chromic acid, the fact that it doesn't start with hydro tells me it's a polyatomic ion acid. It's a ternary acid. It's an oxo acid, however you want to call that. Let's take a look at one more. Once again, I should have the AQ here. I apologize. All right, but I see HNO2. And so since NO2 I know is a polyatomic ion, I'm not going to start with hydro. I'm going to start with the root of the element, or root of the polyatomic, which is nitr. And then I'm going to change ite. Since it's ite, I'm going to change it to us. So it becomes nitrous, and then I just add the word acid. So nitrous acid would be that name. Our last slide here is hopefully gonna kind of nail home or nail drive. I'm looking for a saying there. I've got nothing. Hammer home, or whatever you want to say, the point between binary acids and oxoacids. So I have on the screen here 3 acids that look very similar, but they're going to have different names. First of all, I want you to see, I'm going to do a little divide here. This over here is a binary acid because it only has 2 elements, hydrogen and chlorine. Over here, these are oxoacids because it's hydrogen bonded to some sort of polyatomic ion. There's a lot of craziness. Okay, so different naming rules. So remember, with a binary acid, you always start with hydro. Look at the element, take the root. So chlorine is going to just come chlor. And for binary, you always end in ic. There is never a question about a different ending because it's only coming from an element. And there is only one element that sounds like chlor, and that's chlorine. So we don't have to distinguish. So it becomes hydrochloric acid. For these 2 acids over here, even though they have hydrogen at the beginning, we're not going to start out with hydro. We're going to go straight into the polyatomic ion. So you have 2 polyatomic ions here that look very similar, ClO2 and ClO3. ClO2 is the polyatomic ion chlorite, whereas ClO3 is going to be chlorate. Okay, so notice if I take the root of both of those, they look very similar, don't they? Chlor. And so if I end both of them in ic, there's going to be no way to distinguish between the 2. So this one, because it ends in ite, I'm going to change that to chlorous acid. Whereas the one over here, since it ends in ate, that's going to be chloric acid. So look at the differences. We have hydrochloric acid, chlorous acid, chloric acid. All 3 have very different formulas. I lied to you. There's one more slide, but this slide it's more of just a terminology to be aware of. There's what's called monoprotic acids and polyprotic acids. They're basically just a way of describing how they ionize. And so hopefully you're familiar with the prefixes mono meaning one, poly meaning many. And so that's very general. You can have diproduct, you can have triproduct because they're being more specific, but polyproduct is like the general, the many product. Well, what does product mean? Product actually comes from the word proton, which is the same thing as a hydrogen ion. And you say, how is that? Like, why is that true? Well, think about it. What is a hydrogen atom? A hydrogen atom is something that has 1 proton, 0 neutrons, and 1 electron, if it's neutral. But if it becomes an ion, which means it's a positive charge, that electron goes away. And so really, you have actually 0 electrons now. So notice a hydrogen ion is the same thing as just saying 1 proton. So that's why we say product is the same thing as a hydrogen ion. So if you have a monoprotic acid, this basically means you have 1 proton or 1 hydrogen that is ionizing. And remember, it's always the hydrogens at the beginning of the formula that are ionizable. So notice, HNO3 has 1 hydrogen. HCl has 1 hydrogen. Even this crazy thing, yes, there are 3 hydrogens here, but they're not written at the beginning. It's just the beginning hydrogens that are ionizable. All 3 of these have 1 hydrogen, and so therefore they're classified as monoprotic acids. Polyprotic acids are ones that have more than 1 ionizable hydrogen. So for example, H2S, it has 2 hydrogens, so it's polyprotic, and specifically we would say it's diproduct. H3PO4 is also polyprotic because it has more than 1, and we would say specifically that is a triprotic acid.